In this lecture, we will be looking at polynomial curve sketching, which again is a natural culmination of the material we've learned in this differential calculus course. Essentially, we bring together the information we get from the function's first derivative, and the function's second derivative. We use that information to get a graph of the function. And with that information from the function, from its first and second derivative, we can actually get quite a bit of information about what the function looks like. Now, the first thing we want to address before we do that is our limiting behavior for a polynomial. If we take a general polynomial, so this is just a generic way of writing a polynomial. The a sub n's are the coefficients, those are just numbers, and then you see you have the highest power of x is to the n power. Highest power, the second highest is n minus 1 down to 2, and then we should have an x here. Power is 1 and power is 0. And the question is, what's happening as x approaches both infinity and minus infinity? And the way we can determine that is by rewriting the polynomial in this way. Notice that all we've done here is factor out an x to the n. If you take this expression and multiply the x to the n out through all the terms in the square brackets, you will see that you will recover what you have here up top, p of x. But as x goes to infinity, either plus or minus infinity, the way we've written it here, all of these terms are approaching 0. So it is the a sub n and the x to the n that determine what happens. First, let's think about the case where you have a positive a sub n. In that case, the limit as x goes to infinity of f of x, your leading term is an x to the n. An is positive. For x going to infinity, x to the n is blowing up in size, so this limit is infinite. As x goes to minus infinity, we have to break cases down. So note that a sub n is positive. If x is going to minus infinity, the x term here being raised to the n power is negative. And so we have different cases that depend if n is even or odd. If n is even, you have a positive a sub n, and then x is negative, but it's being raised to an even power. So the result is positive. Since x is going to minus infinity, it's getting huge, and then the n power being even is making it positive, so we get infinity. If n is odd, say 3 or 5, then you have large negative numbers raised to odd powers. The result is an odd number times a positive number. Sorry, not an odd number. The result is a negative number times a positive number, and so we have it approaching minus infinity. We do the same type of case here when an is negative. If an is negative and x is going to positive infinity, x to the n is huge. So you have something huge and positive times a negative, so we go to minus infinity. And we have the same type of issue when f goes to negative infinity. It will depend on the even or oddness of n. So again, reason it out. An is negative. If n is even, you have a large negative number raised to an even power, so you get something positive. Positive times negative will be negative, and so the limit is minus infinity, and infinity in the odd case. So in the odd case, an is negative. You have a large negative number raised to an odd power, So you get a negative times a negative, which is a positive. And note, for polynomials, this is always the case. A polynomial eventually takes off as x goes to infinity. It also eventually takes off as x goes to minus infinity. It's just a question of, does it blow up upwards or does it blow up downwards? This is by no means anything that you need to memorize. You can reason this out with each problem, but this is the idea. So let's look at our first of two examples. We're given a polynomial, and we're asked to basically figure out everything we can from the function itself, its first derivative, and its second derivative. So find the critical points, classify them, determine where the function is increasing, where it's decreasing. Find the inflection points, and find out where it's concave up or concave down. Building on what we just said, we check the limiting behavior. We note, in this case, as x goes to infinity, again, we care about that leading term, which is the highest power of x. As x goes to infinity, x cubed is blowing up to positive infinity. So the polynomial is taking off to infinity. As x goes to minus infinity, we have a large negative number raised to an odd power, which will be negative, so the function is taking off to minus infinity. Okay, so that gives us our limiting behavior. Now let's move into the critical point section. So we take the derivative, and then we factor it. This is the result. And then we check where f prime of x equals 0. So that means 3 times x minus 3 times x minus 1 equals 0. And so solutions are x equals 3 and x equals 1. We want to find the points themselves. So f of 3, and remember, we can remind ourselves, f of x was x cubed minus 6x squared plus 9x. So plugging in 3, we get 3 cubed, or 27, minus 6 times 9, which is 54, plus 9 times 3 is 27, which adds to 0. Then we get f of 1, which will be 1 minus 6 plus 9, or 10 minus 6, or 4. So our critical points are the points 3, 0, and 1, 4. And we want to now identify these with using the first derivative test. So remember, the idea is when you solve for critical points, these are the set of points, the complete set of points at which the function may have extrema. So now that we have these, let's use the first derivative information to figure out, but we'll classify them as extrema if they are, and then we'll figure out where the function is increasing and where it's decreasing. So remember, we have our graph, or our chart. We want to find the sine of f prime. And we write the factors. And then in the middle here, we put the values in increasing order. So we have 1 and 3. And we will then check on either side of these for the sine of these terms and obtain the sine of the first derivative. So we need a number below 1. How about 0? We plug in 0. We get 0 minus 3, or negative 3, times 3 is negative 9, which is negative. If we plug in 0 here, we get negative 1. A number between 1 and 3, how about 2? We would get 2 minus 3 is a negative 1, so that would be a negative 3. We have a negative. Here we get 2 minus 1 is 1, which is positive. And then a number above 3, how about 4? 4 minus 3 is 1, times 3 is 3, positive. 4 minus 1 is 3, positive. And then we multiply. Negative times negative is a positive. Positive times a negative is a negative. Positive times a positive, positive. And we're able to see that the function f is increasing from negative infinity to 1 and from 3 to infinity. So we can write that as f is increasing on minus infinity 1, union 3 infinity, and it's decreasing on the interval 1, 3. We can also use this to identify these as local extreme values with the first derivative test. So as we approach 1 from the left, f prime is positive, so the function is increasing. It levels off at x equals 1, and then it's decreasing afterwards. So we see that the point 1, 4 is a local maximum. And for the other point, as we approach 3, x equals 3 from the left, the function is decreasing, levels off, and then is increasing afterwards. So the point 3, 0 is a local minimum. So now we've identified the extrema. We've identified the intervals where the function is increasing, intervals where it's decreasing. We move on to concavity information. So we take our second derivative, which is 6x minus 12, and we check for inflection points. And remember, at an inflection points happen when either the second derivative doesn't exist, not an issue with a polynomial, or where the second derivative equals 0. So 6x equal 12, or x equal 2. And we check again for the sign of f double prime, just like we did with the sign of f prime with the first derivative test. The issue is now we just have one point where it can change sign. And again, of course, your f double prime, it's just 6x minus 12. We don't have any factors besides this 1. And pick numbers to the left and to the right of where it has a root. Something to the left of 2, how about 0? 6 times 0 minus 12 is negative. To the right, something bigger than 2, how about 3? 6 times 3 is 18 minus 12, positive. So we conclude that f is concave down on minus infinity 2, and f is concave up onto infinity. And we have an inflection point at x equal 2. And remember, f of x was x cubed minus 6x squared plus 9x. So if we want the y value, f of 2 is 2 cubed, or 8, minus 6 times 4, which is 24, plus 18. 8 and 18 is 26. 26 minus 24 is 2. So the inflection point is the point 2, 2. So we've gotten all the information available in the second derivative. And we can now put that together. We summarize all the information that we've gotten, and we can draw the graph. So we have a local max at the point 1, 4. we have a local min at the point 3, 0. We see that the function is increasing coming from the left up to this point. Why don't we put in what's our y-intercept? Remember again, the function was x cubed minus 6x squared plus 9x. If we plug in x equals 0, we get 0. So we see that it actually does go through the origin. So we see, oh yeah, we're going to go through the origin. And we know the function takes off to negative infinity. As x goes to minus infinity, the function is going down to minus infinity. Our inflection point happens at the point 2, 2. And we know our function is concave up to the left of this, to the right of this point, and concave down to the left. And again, we know the function is increasing from negative infinity to 1, decreasing from 1 to 3, and increasing from 3 to infinity, and taking off to infinity as x goes to infinity. So we can put this all together now and draw the graph. And so we'll get something that looks like this, and then we want that concavity to switch there at that inflection point. And this gives us our graph. And so again, we've taken all the information from the function itself, its first derivative, and its second derivative, and put it together to graph the function. Again, very standard type of question in a differential calculus course. Let's do another one that's a little bit more involved. We now look at our second example. So this is a higher degree polynomial, and the result will basically mean that we have more critical points than the first example. But we're going to go through the same exercise. Find the critical points, identify them. Where is f increasing? Where is it decreasing? What are the inflection points? Where is it concave up? Where is it concave down? And we'll graph it. So the first step here, limiting behavior. Now remember, it's the leading term that determines this with these polynomials. So our leading term, 3x to the fifth. As x goes to infinity, we have a positive 3. X to the fifth is also going to infinity, so this takes off to infinity. As x goes to minus infinity, we have a positive 3, but then x is negative, so we have x to the fifth being large and negative, and so the function takes off to minus infinity. So as x goes to infinity to the right, the function will be taking off to infinity. As x goes to negative infinity to the left, the function will be taking off downward to minus infinity. Let's now get our critical points. So we need the derivative. So f prime of x is 15x to the fourth minus 75x squared plus 60. And remember, we have to do the first derivative test to find where it's increasing and decreasing. So we might as well factor this as much as we can. We see we can factor out a 15. So we get x to the fourth minus 5x squared plus 4. This will factor further to 15 times x squared minus 4 and x squared minus 1. And those, of course, factor, again, because of the difference of two squares, x plus 2, x minus 2, x plus 1, x minus 1. And so that's our nice factored form of f prime of x. Setting f prime of x to 0 gives us solutions, and we can read them off right here. We have x equals 2, x equals minus 2, x equals minus 1, and x equal 1. So those are the x values for the 4 critical points of this function. And we then move on to try and identify these via the first derivative test. Now notice I've also evaluated the function to get these values. We can do that quickly here. F of 2 is 3 times 2 to the 5th. So 2 to the 5th is 32. Minus 25 times 2 cubed, which is 8, plus 60 times 2. So this is 96 minus 200 plus 120. (120 minus 200 is negative 80. 96 minus 80 is 16. And so that gives us the point 216. And we do that for each of these. You see, if you plug in minus 2, you'll actually get a similar number, just it'll actually be the negative because all these powers of x are odd. So that's why we get minus 2 minus 16. And then when we plug in 1, we get 3 minus 25 plus 60. 60 minus 25 is 35, plus 3 is 38. So that gives us 138. And similarly, when you plug in x equals minus 1, you'll get the negative of this. So we get minus 1 minus 38. So those are our 4 critical points for this function. We have them listed here. And again, we want to now set up the first derivative test to determine the sign of the first derivative. So we want the sign of f prime. And again, as usual, list these factors. So we list all the factors that make up f prime. And then we put our x values for the critical points in increasing order here. So we have the smallest is negative 2, then minus 1, then 1, then 2. And we make our chart. And again, go through term by term, plug in values. So let's pick something smaller than minus 2. How about minus 3? This would be a minus 3 plus 2. That would be a negative 1, so that will be negative. Minus 3 minus 2, that would be minus 5 or negative. Minus 3 plus 1, negative 2, negative. Minus 3 minus 1 is negative 4, negative. So those terms are all negative to the left of negative 2. Something between minus 2 and minus 1, how about minus 3 halves? Minus 3 halves plus 2 is 1 half, so that will be positive. Minus 3 halves minus 2, that's negative. Minus 3 halves plus 1, that's negative a half or negative. Minus 3 halves minus 1 is minus 5 halves or negative. Something between minus 1 and 1, 0 is nice. 15 times 0 plus 2, positive. 0 minus 2, negative. 0 plus 1, positive. 0 minus 1, negative. Something between 1 and 2, say 3 halves. 15 times 3 halves plus 2 is positive. 3 halves minus 2, that's negative a half or negative. 3 halves plus 1, it's 5 halves, positive. 3 halves minus 1 is a half or positive. And then finally, something above 2. Let's choose 3. 3 plus 2 is 5. That's positive. 3 minus 2 is 1. Positive. 3 plus 1 is 4. Positive. 3 minus 1 is 2. Positive. Now we can work our way up through multiplication. And again, the reason this is happening is to go from these terms to f prime, we're moving up and multiplying them. So 4 negatives multiplied results in a positive. 3 negatives and a positive results in a negative. 2 negatives, 2 positives results in a positive. 2 positive, negative, positive results in a negative. And 4 positives results in a positive. So that's a lot of information, but we can now use this top row to see that anywhere the sign of the second derivative is positive, our function is increasing. So f is increasing on negative infinity to negative 2, union minus 1, 1, union 2 to infinity. Then it is decreasing on the intervals where this first derivative is negative, namely minus 2 to minus 1, and 1 to 2. Note that we also now can identify our extrema. So our local max values, those happen when we go from a positive derivative at a critical point to a negative derivative. So the function's increasing to the left of negative 2, and then it's decreasing after. So we have a local maximum when x is minus 2. And then we have the same kind of behavior here at x equals 1. And our local minima occur where the sign change goes the other way. So here we're decreasing to the left of minus 1 and increasing to the right. So we have a local minimum at x equals minus 1. And similarly, a local minimum here at x equals 2. So 2, 16, and minus 1, minus 38 are our local minima. Now that we have all the information from the first derivative, let's move on to the second derivative. So first, let's differentiate f prime, to get f double prime, which is 60x cubed minus 150x. And of course, it's always best to factor these. So we can take out a 30x nicely to get 2x squared minus 5. And remember, we want to check for zeros, roots of the second derivative. Those are the points where we can have inflection points. So f double prime of x equals 0. We can see from our factored form here that that happens if 2x squared minus 5 is 0, or 30x equals 0. 30x equals 0, of course, gives us the solution of x equals 0. 2x squared minus 5, that's 2x squared equals 5, or x equals root 5 over 2, or x equals minus root 5 over 2. Root 5 over 2 is about 1.58, which will help us because we're going to be graphing this shortly. But of course, we need the sign of the second derivative in order to figure out the concavity properties of our f. We have that second derivative written as the product of these two terms. So we make our chart. And remember, we then want to put our possible inflection points here. So we have the smallest is negative root 5 over 2. Then 0, then positive root 5 over 2. And then we go through and check values in these different ranges. So let's start here to the left of negative root 5 over 2. Negative root 5 over 2 is about minus 1.6. So how about negative 2? 30 times negative 2 is minus 60, which is negative. Negative 2 squared is 4, times 2 is 8. 8 minus 5 is 3, which is positive. Something between minus root 5 over 2 and 0, negative 1 is in there. 30 times minus 1, negative. 2 times minus 1 squared is 2, minus 5 is negative 3, so that's negative. Something between 0 and root 5 over 2, 1 is there. 30 times 1, positive. 2 times 1 squared is 2, minus 5 is negative 3, negative. Something above root 5 over 2, how about 2? 30 times 2 is 60, which is positive. 2 squared is 4, times 2 is 8, minus 5 is 3, positive. Multiplying up, we get positive times a negative is negative. Negative times a negative is positive. Negative times a positive is negative. And positive times a positive is positive. And we thus see that f is concave down on the intervals where the second derivative is negative. So we have downward concavity on minus infinity to minus root 5 over 2, the leftmost interval, and then also from 0 to root 5 over 2. And then f is concave up on the intervals where the sign of the second derivative is positive, so minus root 5 over 2 to 0. And then from root 5 over 2 to positive infinity. And this means we have inflection points at all of these values. X equals minus root 5 over 2, x equals 0, and x equals root 5 over 2. And to get the y values, you can plug these in to the original function. Putting this all together in a summary, we've identified our local minima and our local maxima, 2 of each. We've identified the intervals on which f is decreasing and the intervals on which it's increasing. We've got its upward and downward concavity and its inflection points, and then we also have the behavior when x goes to positive infinity and x goes to minus infinity. And we can put this all together to graph the function. So putting this together, in a separate plot, let's try and include all that information. So we have these points happening at x equals minus 2, minus 1, 1, and 2. And then we have y values of concern of 16, minus 16. So the scale will be different for the two axes. And then 38 and minus 38. So recall here, we had local minima at minus 1, minus 38, and 216. So minus 1, minus 38, down here we have a local minimum. And at 216 here we have a local minimum. We had local maxima at 138 and minus 2, minus 16. So minus 2, minus 16. we have a local maximum. And at 138, we have a local maximum. We also know the function actually does go through the origin. So we have this point as well. And actually, we can be even more specific. That is an inflection point. So let's come back now and try and start to draw it. So first of all, the limit as x goes to minus infinity of f of x is negative infinity. So as x goes to the left, the function has to blow downward to minus infinity. So we know the function has to look like this. Similarly, we saw that the function blows up to positive infinity as x goes to infinity. So we know we're going up this way. And this is, of course, consistent with our increasing, decreasing information. So we were increasing from negative infinity to 2, and also from 2 to infinity, which is consistent with what we just drew. We're also increasing from minus 1 to 1. We saw we had this local minimum here. We're increasing and changing concavity at the origin up to this point 138, which is a local maximum. So we can see that the function should look something like this. We're concave up here, and then we switch to concave down at that point. Let's draw our other inflection x values. So remember, we had 0, but we also had x equals minus root 5 over 2 and root 5 over 2. And recall that root 5 over 2 was about 1.58. So around 1.6, we should have those inflection points. So a little right about here. So we should have an inflection point right about here. And right about here. We also said that the function was decreasing from minus 2 to minus 1. So we see we want to draw here with the function decreasing, but we have to switch the concavity at this orange point. So we go down here and then switch that concavity. And we have a similar trend here where the function is decreasing from 1 to 2 and changing concavity here at this orange point. So we go down like this. And so that takes all of the information that we summarized with our analysis and graphs the function.